Okay, so question 11, neopentane has the alternative name of what? So first you need to know neopentane. I think of neopentane as a functional group more often. So it's a functional group that looks like this. So that's a neopentyl group, but just neopentane itself looks like this. So that means we have 1, 2, 3 carbons if we're going to name it. So propane. And then there's 2 substituents right here in the middle. So 2,2-dimethyl propane. So that answer is answer choice C. Which of the following organic compounds has the strongest base? So the strongest base is the weakest acid. And the weaker acid has the larger pKa. So 52, that's your right answer. That's the strongest base. If it had the conjugate base, it would be the strongest base. Okay. What is the correct IUPAC name for the following compound? So I'm just going to try to find the longest parent chain. 1, 2, 3, 4, 5, 6. If we went there, it'd stop at 7. So 7, 8 is definitely better. So it's octane. We have to consider both numbering systems. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, just looking at this, alkene is a higher priority than bromine or alkane groups. So it actually does need to start there. So one of our substituents is 1-ene. And then we have 3-methyl, 6-methyl, and 7-methyl. Then we have 4-bromo. So then you combine all this. You have 4-bromo, because of alphabetical order, it comes first. 3,6,7-trimethyl, oct-1-ene, or it can be 1-octene. Either of these is right. So the right answer choice here would be answer choice C. Okay, the next question, which reaction shown below would favor the reactants left side of the reaction over the product's right side? So basically, which of these is written correctly? That it's going to favor this side, or which of these is written incorrectly? That it would favor this side over this side. So in which of these would the arrow actually be pointing this way, is what this question is asking you. And this is your low to high, it will fly. So if it has a lower pKa on the left side and then goes to a higher pKa on the right, it's going to stay facing this direction. But if it's backwards, it's not going to go that way. It'll go the other way. So lower pKa on the left, higher pKa on the right. That's because this is a weaker acid, and a weaker acid is more stable. It's less reactive, so that wants to be on the product side. Okay, so here we have, I'm going to identify the acid. So this was OH, and here it's O minus. So the acid and the conjugate acid, this is the base, that's the conjugate acid. pKa is 16 to 18. pKa of this functional group is usually around 50. So this is good. It would react this way, so it's not our right answer. This is our acid, this is our base, so this is our conjugate acid. So this pKa is 25, and this is 15.7. So this is high to low, it won't go. So I think this is a good answer, but let's check all of them just to be sure. This is 15.7, and this is 50. What? This is 25, not 50. This is 25. So this is low to high, it will fly. So that one is going to react forward. It's not the answer we're looking for. This is 16 to 18, and H2, I think, is that around 30-ish? I think. I don't know for sure. I don't have that one memorized. I should double check and get that in my brain. But this is definitely bigger than alcohol. I know that for a fact. So that's going to proceed the way it's written. So it's not going to be our right answer. And then here we have a carboxylic acid and an alcohol. So low to high, it will fly. So the right answer is B. Okay. And last but not least, 15, rank the boldface hydrogens for the following compounds from most acidic to least acidic. So this is going to be 25. This is 4 to 5. This is, this isn't 25. I'm crazy. This is 45. This is 425. This is 25. This is 50. And this is about 9. So if we're just looking at these functional groups, this is an alkene, carboxylic acid, alkyne, just a regular sp3 hybridized alkane, and ammonium, not ammonia. So be sure that you know these functional groups off the top of your head. They're going to come up. So this is the lowest, then 5, then 3, then 1, and then, did I have that in the right order? And then 4. Okay, so I think D is the right answer. But if you just know, if you're not sure on this and you just know that carboxylic acid is more acidic than an alkene, then you can get rid of these automatically. And if you know that carboxylic acid is more acidic than ammonium, you can get rid of these. And then you just narrowed it down to these two. And you can look at the next point of difference. So 3 or 5. Is an alkyne or the ammonium more acidic? Well, ammonium has a positive charge, so that's probably going to be more acidic. So just based on that, you can narrow it down to answer choice D, which is the right answer. Okay, that completes the multiple choice part of this. Let's go into the free response question. So draw the mechanism for the following acid-base reaction in the boxes provided. Circle the side of the reaction that is favored and explain why. So usually if there's a negative charge, that's going to be more basic. And then the other thing is going to be more acidic. So this lone pair would attack this proton and leave the lone pair behind that was part of this bond. So the right answer is the CH2 minus has gained a proton, so it's CH3 now. And your nitrogen now, it already had a lone pair beforehand. We won't count off if you didn't do both, but at least has one additional lone pair and a negative charge. So that's the mechanism for the acid-base reaction. Then we're going to circle the side of the reaction that's favored. So this is again about comparing acidity and pKa. So the pKa of this is 38, and the pKa of this is 50. So when we're thinking about which side is favored, the weaker acid is going to be favored. So if this is the base and this is the acid, this is the conjugate acid. So the larger pKa will be favored because it's more stable. The other way you can think about it is low to high, so smaller to larger, it will fly. So it's going to go this direction. So really the proper arrows would be more like this. It's still in equilibrium, but really it's significantly favored to go this direction. And this side is favored. Okay, so did I do all the parts of that? Draw the mechanism, circle the side of the reaction that's favored, and explain why. Yep. Okay, so this question, draw all the resonance forms. So I've seen students kind of try to do all the resonance forms at once, where they'll move something and move a bond and move a bond and move a bond. I recommend you go one carbon at a time. So if you try to move this lone pair up here, it's going to form a double bond, but there were already 3 implied hydrogens here, which means there's 5 hydrogens to this carbon, and you can't break any of those bonds, or then it wouldn't be a resonance structure anymore, right? One of the rules of resonance is you're not breaking bonds or you're not moving atoms. So you can't break a bond to move any of those atoms. And the same thing would be true if we go down there. So neither of those is an option. So the only other place we could go is right here to form a double bond. And if we do form that double bond, then there would be 1, 2, 3, 4, 5 extra double bond here, bonds to that carbon. So another one of these has to break. And if I'm breaking a double bond, I know that this will have a full octet right here because I'm filling in a double bond on this side. So the only thing that wouldn't have a full octet anymore if this double bond went away was right here. So I'm going to move the lone pair right here to fill up that octet. And I've seen students struggle with this until they do it on their own. So I recommend you stop right now and try to draw this structure where these electrons are going based on these arrows. This lone pair turns into a double bond right here. This double bond breaks and goes right here. You try to draw the next structure and then turn on back the video and see if you get it right. So the bond that was here broke and went here. These two we didn't mess with. Now if this bond goes here and this breaks, because if we put this lone pair here, we'd form a double bond, but then this already has an implied hydrogen. So there'd be 1, 2, 3, 4, 5 bonds to this carbon. So the next thing has to break. So if we did that, we didn't mess with this bond over here. We didn't mess with this bond over here. Those are the same. But we formed a new bond right here, and our lone pair went right there. Oh, sorry. The lone pair goes right there. You can draw the negative charge moving around there. So if you have that lone pair right there, that fills up the octet of this carbon with this one's all been filled in by the double bond. So they're all full octets. This just has a negative formal charge. Now, the only other place you could go with this is here. And if you did that, this already has an implied hydrogen. So 1, 2, 3, 4, 1, 2, 3, 4, 5 bonds. If you had the other double bond there. So this has to break and the lone pair go here. And there you go. That's the resonance structures that are moving all the way around. Now, there could be a resonance structure with this nitrogen, but I'm not going to get into that right now. If you did it, you got extra credit points, but this should be, this was all that we were looking for right now, was just moving all the way around. Now, if you did the curved arrows to make this lone pair become a bond there and this move over, that's fine, but you just end up back with this structure. So, okay, rank the acidity of the following molecules from strongest to weakest, with 1 being the strongest and 3 being the weakest. Okay, so you can, if you know the pKa's of these things off the top of your head, you should know this is 4 to 5, this is 9, and this is 16 to 18. So phenol is a specific pKa that you should have memorized. But even if you didn't have those memorized, you could still get those answers through the reasoning. And we want you to be able to reason through this. So why is carboxylic acid more acidic than either of these alcohols? There's 2 reasons. One, there's an inductive effect of this electronegative atom pulling electronegativity towards itself, creating a partial positive right here, so that if this proton goes away and you're left behind with all these excess electrons, it would be distributed. But also there's a resonance structure right here, right, where the oxygen is negative and there's a double bond over here. So, and then you have your benzene ring. Sorry, that's not a great drawing. But so you have the double whammy of resonance and inductive effect. The next one, this oxygen, or this alcohol, phenol, is known to be more acidic than regular old alcohols because this also has a resonance structure. The lone pair can go down here, and you get a lone pair right there. Basically very similar to the other problem that we just did. So now the negative charge is delocalized here, and then it'll go there and break this bond. And you have, let's see, a bond here, a lone pair here. So now the pairs delocalized on 1, 2, 3 different atoms, and then this lone pair will go here, and this will break, and you'll get all these. So you have resonance going on here that makes this more acidic than a regular alcohol. Now, if you lose these protons, this alcohol, you actually can't do a resonance structure here. Why? Because there's already 1, 2, 3, 4 bonds here. If you make a double bond, there's none you can break without losing any atoms. So because of that, it's not in resonance. So 3 doesn't have resonance or inductive effect. It doesn't have another dipolar atom around here. So this has the double whammy of resonance and inductive effect. This has resonance, and this has none of that. So you're going to be able to reason through the pKa's that you've already memorized, hopefully. Okay. Draw the following molecule in bond line form. So I start with the parent chain. Decane, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you can just start numbering from whatever side you want to, as long as you put all of these in the right position. So I'm just going to start from this side. 8 chloro, 6 ethyl, 8 isopropyl. I'm going to put it down. You can put them both pointing up. It doesn't matter. 2,2-dimethyl. You can put them both like this, or you can put one pointing down. It doesn't matter. Dec 9-ene. Decane's 10. I'm crazy. Okay. I saw this 9. I was like, decane, 9. Nonane is 9. Decane's 10. Okay. And the way I knew that was because 9-ene wouldn't be right, because it would start from here, and then that should be the end of the double. It should start with 8. It would be 8-ene if it was that position. So that's how I got that right. That's how I caught my mistake. So 9-ene, 5 all. And that should be all of it. 8 chloro, 6 ethyl, 8 isopropyl, 2,2-dimethyl, dec, so 10-ene, 9-ene, 5 all for the alcohol. And the reason we start from, even though the double bond has a lower number, starts at 9, if you started this way, it would be 1, but then your alcohol would be 6, and alcohol needs to have a higher priority, so instead it's 5. Okay, so that is your exam. I hope that was helpful to you guys. I'll also post the key online, and I hope you have a great week.